An imaginary number. The basic problem we have in mathematics is a square root of a negative number. So I will look at the most basic square root of -1. Now, when we talk about the square root of a number, it's asking a specific question. And that question is, what number times itself exactly 2 times is -1? So let's think about that. What number times itself twice is -1? There is none, because if I take a negative number and multiply it by itself, which would be another negative number, my answer would be a positive number. If I was to take a positive number and multiply it by itself, I will also get a positive number. So no negative number times itself is negative. No positive number by itself is positive. If I take 0 times 0, I will get. So basically what I've just said is no negative number will work, no positive number will work, and 0 doesn't work. That is, all of the real numbers do not work. So this is not a real number. If it's not a real number, then we're going to call it imaginary. And because imaginary begins with the letter I, we will denote the square root of -1 as the number I, which is not a real number. So we've got square root of -1 is I, the imaginary number I. However, even though it's imaginary, it has some properties that are consistent with all other numbers. For instance, I have an equation here. I should be able to add, subtract, multiply, divide, or take any exponent to both sides of that equation. I'm going to take this equation and I'm going to square both sides. Let's take a look at this. So, the square root of -1 squared equals I squared. Well, the square root of -1 times the square root of -1 is -1. So even though I is an imaginary number, I squared is a real number. Everyone okay with this? Why is I squared a -1? Let's look at our property of exponents, maybe to explain it a little bit better. A square root can be written as a fractional exponent. That's the same as the square root of -1. One's written with a radical symbol, one is written with a rational exponent. So if I square these, let's take a look at -1 to the 1/2, which is really the square root of -1. And take both sides and square it. With exponents, it becomes a little bit easier to see the process. What am I going to do with these exponents? I'm going to multiply the 2 times the 1/2. Property of exponents. When I multiply 2 times 1/2, I get -1 to the first, which is just -1. So if you bring down this side, then I have, when I square something, I simply remove the radical shown with the property of rational exponents. Yes?
So you're saying this when you the square root is the opposite of squaring a number, right? So then when you square it, you cancel out the square root symbol, basically?
Yes, squaring is the opposite of the square root. And basically it's easier to see it with the property of exponents, because what you're really doing is removing it because when you multiply those two exponents, I end up with a 1. It's not, canceling is not the best word because that seems like you remove and end up with a 0.
Okay.
But we multiply it out, and like I said, it's much easier to see it. That's one of the reasons why we study exponents and radicals switching back and forth. It's a lot easier to see the math work. So, there I have it. An imaginary number squared is a real number. So, we're going to talk about now a complex number. Okay. Any number that can be written with an imaginary component is called a complex number, where A is a real number, or the real component, and BI is the imaginary component. An example of a complex number is this, 2 plus 3i. That is a complex number that has a real component, 2, and an imaginary component, 3i. So we're going to do some mathematics with complex numbers. First, we're going to talk about adding and subtracting complex numbers, and then multiplying complex numbers. And then, last but not least, we'll talk about rationalizing a complex fraction. So, if I take two complex numbers, let's take this number, 2 plus 3i, and I add 4 minus 2i to that number. So I have two complex numbers, the 2 plus 3i, and the 4 minus 2i. When I add them, we're going to add and subtract with the I, just like any other value, including the value x. So if you add or subtract with 3x and a negative 2x, it's exactly how we're going to handle the I. So we're going to combine like terms. The 2 and 4 are like terms, so 2 plus 4 is 6. 3i plus a negative 2i will be handled just like 3x plus 2x, giving us one of those objects remaining. So all we're dealing with is the lead coefficient 3 and adding the negative 2, giving us 1i. You do not need to write the 1. However, it's not wrong if you do. Everyone happy with this? There is no multiplication there. This is pretty much the same technique if I took 2 plus 3x plus 4 minus 2x. I'm just combining like terms with addition. Combine that. Combine that. So same technique as if it was an x or a y or any other variable. However, I is not a variable. I is the square root of negative 1. But the mechanics are held the same as if it was a variable. So, if we were multiplying, however, well, not however, it would still be handled just like a variable. I would use a FOIL technique to distribute this multiplication. So, I would end up with 2 times the 4, 2 times the negative 2i. I would take the 3i times the 4 and the 3i times the negative 2i, and I would handle it just mechanically at first like if it was a variable x, giving us a negative 6 I squared. Now I will combine like terms and simplify. So I have an 8 plus 8i minus 6, but that I squared can be simplified to -1, which means I can further simplify. So I have 8 plus 8i plus 6. Now I have like terms. The 8 and the 6. And I have written my final answer in complex format. Yes, ma'am.
You have to write the real number
First?
first.
Yes. Always have to write the real number first because we want our final answer in this format here. The A plus the BI whenever possible. Now, the only modification would happen, the only modification if you're dealing with square roots. For instance, if I had a number that looked like this, and I want to write this number as a complex number in the standard form, what I will do is separate out this negative square root of, the square root of -1 and the square root of 5 as two separate values. The square root of -1 I will write as I. Now, there's a reason why we have this slight modification with the I in front instead of the I behind. Because of a radical, it's possible to get confused whether the I is inside the radical or not supposed to be inside the radical. So we slightly modify our format for clarity. By putting the I in front, we know we're not taking the square root of that I. Everyone clear on that? So it's a slight modification, but there's a reason. We always do that with square roots, put values that are not supposed to be in the radical in front of it. Now, let's see. One more example, and that is how to remove imaginary numbers from a denominator. Basically, what we're going to use is this principle here, and that is the difference of perfect squares. In intermediate algebra, you went over that this property gives you a squared minus b squared when we FOIL that out. If we look at that and utilize it for this example, I've got another property that says I can multiply anything I want to, the numerator to the denominator, as long as I do it to both, and it will not change the value. That is this property here. Let's see, that's an AB times C over C is still the same. Doesn't change the value to multiply the top and bottom. We use that all the time in fractions to be able to get a fraction with a common denominator. Well, we're going to use that property here to get rid of the imaginary numbers from the denominator. For instance, what I can do with this situation is a perfect square would occur if I had 4 plus I. I'd have a difference of perfect squares. Now, notice, I'm going to slide this up a little bit. What happens on the top is I get a 4 plus I, and on bottom I get 4 4 times 4 is 16 minus I times I squared. I'm going to work from left to right now. The top stays the same. The bottom becomes 16 minus I squared is -1. Leaving me 4 plus I over 17. The last thing I'm going to do is split this into 2 fractions. Leaving me 4 over 17 plus 1 over 17I. Now I have written this expression in complex standard format. I have an A plus BI. Okay, we still have some more work to do on 3.3. That should take you through number 57. So you can do anything I've assigned on 3.3 up to but not including 3.7. I'm